So very good afternoon to all of you. Now we are in a chapter in which we are talking about the pitch of the sound. The pitch is a sensation which that we receive after sound of a particular frequency hits the eardrum. Remember last lecture somebody asked this, that isn't pitch the frequency? Answer is pitch is frequency, but pitch is beyond frequency as well. It's a perception of the frequency which can change under different conditions. So in today's lecture we are going to explore that further. We are going to particularly talk about the pitch of a pure tone. What are the factors that affects the pitch of a pure tone? And also we will talk about the pitch of a complex tone. Towards the end, we are going to talk about the Cbex Siren. Remember, the Cbex is the same person, Cbex effect that you will do in thermodynamics, or that you might have heard or read earlier about it. So we are going to do Cbex Siren, and we are going to look at one simple demonstration somewhere in the middle. So that is the today's task at hand. So let's go ahead with this. So the pitch of a pure tone, remember what is pure tone? The pure tone is a simple sine wave. So if you have a pure sine wave that of a given frequency, it is called as a pure tone. It could be any frequency, any audible frequency from 20 hertz to 20,000 hertz theoretically. Practically, maybe little about 20 hertz and maybe some level, some value less than 20,000 hertz. But as long as it is a pure sinusoidal wave, it is called a pure tone. So we are looking for the pitch of the pure tone, or how does it feel, how does it sound, what are the possible changes, variations in the pure tone. So that's what we are looking at. The pitch and the sound level. So apparently the pitch of a pure tone depends on its sound level. Remember what was sound level? If you recall, the sound level has two sound. We had spoken of sound pressure level and sound intensity level. So right now when I'm saying sound level, I'm just talking about sound intensity level. I'm not talking about sound pressure level. So now we can talk about this. If it's a lower tone, then the tone decreases, the pitch decreases with sound level. So as the sound level increases, the lower tone pitch decreases. Lower tone, low frequencies, bass frequencies, the bass tones, they appear to be of still lower if you increase the intensity of sound. So for example, if a speaker is playing, a drum music is playing through a speaker at a lower volume. Now if you increase the volume, the drum will sound more bassy, more lower in tone. So do remember that. For higher tone, the sound apparently increases with sound level. The tone increases with the sound level. The tone means the frequency, the pitch. So if you make it sound louder, the same instrument or same music or same tone, pure tone, sounds shriller, more sharper. For mid-tone, it is minimal. The change in the pitch is minimal with sound intensity level for mid-tones. If you look at a practical data, that will make some sense more, that what do we mean by lower tone, higher tone and mid tone. So these are the lines for different frequencies starting from 200 hertz, 1000 hertz, 2000 hertz, 4000 hertz, 6000 hertz. So these are the different frequencies. Now if you are at a very low frequency here, then this is the lower tone. So the lower tone, as the sound intensity increases, this is a graph on LP, sound pressure level, not intensity level. So as the sound loudness or sound pressure increases, the 200 hertz tone appears to be lower in tone. The pitch shift in percentage is marked over here. So how much percent it will decrease. If it is a mid-tone is around 1.5k to 2k, then that appears not changing with increase in the sound pressure level. If you have sound pressure level increasing and the frequency is say 6000, which is a high frequency, the frequency may be of a violin, maybe of high notes from guitar, etc. Then if you are in this frequency band, then as the loudness increases, the pitch appears to be increasing with loudness. Remember, actually from the source it is not, but it appears to be increasing. So if you have a high frequency sound playing through a loudspeaker, and if you increase the amplitude, volume, then it appears more shriller. Obviously, these are experimental data which are performed on trained ears, where just by listening to the sound, people can identify what note or what tone is playing. So, the bottom line or main takeaway from this discussion is, as somebody asked the question last time, is pitch not the frequency? Answer is pitch is the frequency, but that's only partly true. You can easily see that as the intensity of the sound is changing, the original frequency will not change, but the perception of the frequency, that is pitch, is going to change with the loudness. Now having said that, this can have its own effect in a musical performance or anywhere. So for example, one of the example is, uh, typically if the performance is happening in a hall or in a theater, in an enclosed place, there's a lot of reverberant sound that we are going to talk later towards the end of the syllabus. So the reverberant sound, as the sound dies off, its intensity drops. Now, as the intensity of the reverberant sound drops, the pitch changes. So you can see that as you go from the intensity from somewhere here to somewhere here, the pitch of many notes are going to change, and that will impact the quality of music that one is listening in these kind of surroundings. So that is one thing. Then the pitch also depends on the duration, how long you hear or play a tone, that decides how it appears to us or how it sounds to us. At least at least two cycles of a given tone has to play, more or less, to make it heard completely. At least two cycles, that is the general practical observations. Remember, I'm talking about pure tones. If you are less than 2 cycles, then it will not appear to be a tone, but it will appear to be clicks. It will not give you the sweet sound of a note. And important thing is that for the short tones, which are very short in time, and long tones, uh, which are more than 2 cycles, the transition will take place, and the transition depends on the sound level. So typically, if the sound is louder, then the transition happens quicker. If the sound is not so loud, transition will take a little longer, maybe 2.5 cycles, maybe 3 cycles. So that is another important thing. I will come to it in a while. Here is my graph which actually represents that how much minimum time does it take for some pure tones to be audible as a pure tone and not as clicks. So you can see that it's typically as a curved graph. So for example, if you are a 100 hertz frequency, it takes around 400 millisecond to 400 millisecond to get heard or sensed completely. And if you have 1000, then you have around uh, it has large number of cycles in a given time, so it has around 10 millisecond time to get sensed completely. However, the equation reverts, because if there are large number of cycles coming too quickly, then it becomes little bit difficult for the ear to get the sense of the tone. Then it averages out a little longer to sense that tone. So that is why the graph rises bit towards the end. Now, apparently, there is something called an acoustical uncertainty principle, which, I mean, you are familiar with one uncertainty principle, or you will get it in your quantum mechanics paper. Delta P delta x is greater than or equal to h cross. There is something in this also, that delta f is the change in the frequency of the sound little bit. Delta t is the time interval for which it plays. So, and delta f is the frequency band, in fact, not change in the frequency, but the frequency band. So, if it's the product of the two appears to have some constraints k, the k value is less than 1 most cases, appears that if your frequency band is large, then it can play for a smaller time to get it recognized, or vice versa. So that is worth exploring. I leave that part for you people to explore further. The pitch and duration, yes. So I have some small demonstration right now. Sorry. So if you are listening to this lecture in a very noisy place, then try to focus on the lecture a little bit more. Perhaps shift to a quieter place or use a headphone, but at a volume less, around 50%, not more than that. So what I'm going to present you is 3 tracks, 3 examples, 3 demonstrations. In each demonstration, I'm going to repeat similar things. I'm going to take a frequency. I will play it for a very small time, say 5 millisecond. Then I will play it for 10 millisecond. Then I'll play it for 20 millisecond, so on and so forth. And then I would realize that how initially what appears to be a click, as the duration increases, gets converted into a tone. You will be surprised that how the sweetness of the sound changes when it changes from clicks to a tone. So let's go ahead. I can't see. No. Yeah. So let's go ahead. I'm playing the first one. You could see that initially what was a click, as the duration of the tone increases, it become a note. I recommend you to listen to this lecture, maybe if not now, maybe later, using a loudspeaker, at least this part, and you will get clearly what I'm talking about. So you could see that the same tone, same frequency, if it plays for a shorter while, it appears different, just a click. It does not give the exact note. But if you go to the towards the end, if you play it for a longer duration, then it gives you a perfect note. I'm playing it again. Yeah, I'm repeating this at different frequencies. When you are listening to this, please don't be cautious about the crow sound which is in the background. That is just an additional audio effect. So this is at a higher frequency than the previous one. Previous one was a thicker sound. This is little shriller. You can see that the same sound played for a longer interval gives you the perfect feeling of the note. This is still higher frequency. I repeat it once again. So you can see that the duration for which you play a given frequency will give you a different pitch sensation. Going ahead from this point onward, okay, fine. We can go to the pitch and the interfering sound. Next idea in the discussion today. So if the interfering sound has a low frequency below of the test tone, an upward shift always occurs. So if you have a test tone, a pure tone, and if you have another sound which interferes with the first one, and if the interfering sound has a lower frequency, has a frequency below the test tone, then the test tone appears to be at a frequency which is higher than the usual. Its pitch shifts upward even though the source keeps playing at its own level. It appears to us at a higher frequency. This phenomenon is something which is very simple. If you um, come out in bright light from a dark room, it appears to be brighter than usual. So that kind of situation it is. Or if you look at a bright and dark section, then the bright section looks brighter than the darker one. If the interfering tone frequency is above that of a test tone, then a downward shift is observed at a lower frequency. This is the reverse operation. So if interfering tone, the remember your pure tone is playing, your interfering tone, the another tone is playing above the test tone frequency. Then in that case your test tone frequency appears at a lower frequency. Its frequency drops, it appears more bassy. So that is the next idea. The third is A low frequency interfering noise always cause an upward pitch shift. So remember, here it is an extension. In the first point, your interfering sound is also a pure sound. Your test tone is also a pure tone. Here, if you have a noise is typically a broad spectrum noise, just that it is focused on the low frequency noise. So if you have a tone playing and if you have a low frequency, then your tone pitch shifts in the upward. When I say upward, it appears to be shriller, it appears to be of a higher frequency. Now, pitch shift increases with the amount by which the interfering tone or the noise amplitude exceeds that of the test tone. So, even that plays a role, that how loud are your interfering sounds. If your interfering sounds are too loud, then the pitch shift is large. If your interfering sound amplitude is not that loud, then your pitch shift is not that large. So even that matters quite a bit. So far about the pure tones. Now we will go for the complex tones. Now, as the name suggests, complex means not pure, not single tone. It's more than one tone. Remember, in day to day life, pure tones are almost never heard unless you are listening to some kind of experimentation. Pure tones are almost never presented to us. Most of the time, the tones presented to us are the complex tone. Now, in a complex tones, if there could be variety of frequencies present, I'm going to restrict this discussion only in one type of complex tones where I have frequencies in a multiple of each other. That is fundamental, first harmonic, second harmonic, third harmonic, etc. So if number of harmonics are playing together, then that is one of the easier complex tones that we can understand easily. So the ear identifies the pitch of the fundamental, even if the fundamental is very weak or missing altogether. So this is one of the most important phenomena that has been observed in case of pitch of a complex tone. That if there are number of harmonics present, but fundamental frequency is not present, fundamental frequency is not there, or even if it is there, is there as a very weak frequency, the ear can identify the fundamental. The idea, this entire idea is referred as virtual pitch. Okay. For example, if your tone has a mix of frequencies, say a complex tone, 600, 800, 1000, 1200, they all are playing together, then your what would be the base frequency, or what would be the base pitch that your ear will observe, or your ear will perceive, the better word to use. So you can see that these are all in multiples of 200. So 600 plus 200, 800, uh, 200 into 6, 200 into 3, 600, 200 into 4, 800, 200 into 5, 200 into 6. So these are all multiples of 200. That means your base frequency is, or the fundamental frequency is 200, but it is not played. This tone does not have 200, does not even have 400. It has only 600, 800, 1000 and 1200. But when you play them together, you can still feel that this tone is very much similar to the 200 hertz tone. 200 hertz tone is very much similar to this. So you can perceive that 200 tone even if it is missing in this combination. This is an experiment which you can do at home in your mobile phone tone generator. You play at 200, then take you need a couple of mobile phones. You have to borrow from your parents, siblings, whomsoever. Take in one, take 600, take 800, take 1000, forget that, and play them together. Record the two sounds and see how closely they resemble. So you can still feel that it has 200. So your 200 hertz is missing here, but still you can make out, and therefore the word we use is called virtual pitch or missing fundamental. So as far as the pitch of the complex tone is concerned, this is one of the most dominant phenomena. In fact, this phenomena can be used by a clever musician or a clever equipment designer to create frequencies which are otherwise not possible. One of the example is producing bass tones by small speakers. Now, remember that to make bass tones, when we do the speaker design, we will find or we will study that to make lower frequency tones, your speaker should be really large. Okay, but smart designers can make even a small speaker produce bass tones or lower frequencies. How do they do it? The answer lies in the virtual pitch. The speakers are small, so they generally play in this range, but by the using the concept of virtual pitch, they may be made sound at a frequency much lower than these ones, and therefore much bassy speakers. So that is what happens. Most of these smaller speakers, portable smart speakers, they try to achieve these kind of things. The last topic of the day is the Cbex Siren, which an experimental work done by Cbex to understand and talk about what we just spoke. A Cbex Siren is a representational diagram is here. It is actually a disc which has perforations here, 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 here. Earlier at the time of Cbex, you used to pump uh, some high pressure steam from the middle. The steam used to escape through these, the puff of the steam used to come out through these sirens, through these holes, giving you a sound. The this was or this was rotated sometimes. So sometimes if puff of the steam was coming say from this hole, but if the disk is rotating, this hole will go off, and then this region will come and the puff will be blocked. Again the disk moves, next hole will come and the puff will be released. So this block and release pattern used to take place, and because of that it used to create compressions and rarefaction and hence sound. Typically the sound used to be very loud from this arrangement. In fact, one of the earlier earlier sirens made by Cbex were used in the industrial towns as alarms or sirens. And if you have noticed, it even plays something similar, a community siren kind of thing plays even at St. Xavier's somewhere nearby at around 9 a.m. So this is how the Cbex siren is there. So rotating disc with periodically spaced holes that created puffs of compressed air at regular intervals. That interval will define that what is the frequency of the sound, and that interval will depends on how fast the disc rotates. So if the disc rotates very slowly, the time interval between two puffs will be long, and therefore the frequency will decrease. If the disc rotates too fast, then the time interval between two puffs will be small, and disc will and the frequency will increase. The sound pitch depends on the time between the puffs of the air. So the frequency or the pitch bass sensation depends on how what is the time interval, which in turn depends on the disc speed. or it also depends on the number of holes. So for the same speed of the disk, if you have more number of holes in the disk, then your disks are closer to your holes are closer to each other, and puffs are released at a faster time intervals, and therefore increasing the pitch. So from this example to this example, you can see the number of holes are higher. Again, from here to here in the diagram, it has been doubled. Here it is, here it is also, I'll come to this later. So it is doubled. So doubling the number of holes raised the pitch exactly by an octave. So if you double it, the pitch will get doubled, increases by an octave. Okay. So in the third case, from case A to case B, it has just been doubled. In A to C, it has again doubled, but in B, it has been symmetrically doubled. All the holes are at equidistant from each other, but here holes are unequal distances. So here the puffs are released at equal time interval. Here the puffs are released at half time interval, but here the puffs are released at unequal time interval, in a sense that the time interval between this puff and this puff is large, but these two is small. But the whole setup repeats at the same time as that of this one or as that of this one. So the whole setup repeats after regular time. Just that the two puffs are asymmetric. Unequal spacing gives pitch same as part A. So here, now what is happening here is, here you will get a frequency F, here you will get a frequency F, here you will get a frequency 2F, here you will get a frequency which is more or less similar to A. That is a surprising thing. It does not get doubled. The pitch does not get doubled. Here the pitch get doubled. Here pitch does not get doubled. It sounds as if it is in the case A, and that is the interesting part. So that actually demonstrates, here again some mathematics of it. So what is happening in the third case is, I can explain it here. This is, although I'm going to hit this topic in the next chapter, but let me briefly introduce. It is the Fourier transform. So in this case, you have fundamentals and other harmonics. Here the frequency gets doubled, so this is fundamental and other harmonic. Next one is not plotted in this. Now here it is not equidistant, so you get this fundamental over here, but this overtone is present, but the fundamental gets missing in this case. So it's a missing fundamental or suppressed fundamental case, but still the sound coming from the siren appears to be of a similar quality or timbre that we are going to talk in the next class as that of in case A. So that is the Cbex Siren for us. It was used for a very long time to produce sound, long alarms, etc., caution alarms. These days we have artificial ways to create loud sound, so we use that. We don't use these techniques, but this is a very important early experimental arrangement to demonstrate the concept of missing fundamental or virtual sound, virtual tone, virtual pitch. Okay, so with this we can stop here. Today's class we can stop.